All right, okay. Hi guys, I'm George Fairbanks, and I want to thank the committee for organizing this great conference and inviting me to come speak with you guys. And some of you, maybe about half of you, were in a tutorial workshop yesterday, and we talked about similar topics. This is a slightly different spin on it. The big idea today is that we have an opportunity when we write programs to use them to let us think more clearly than if we were to do it by ourselves. And so the way I phrase that is that your code is your partner in thought. It seems like a good idea for me to give you a little bit of background about me so that you understand how I got to think about things this way. In my early days, when I was programming, the first challenge was, can I simply write software that works? And we've all been there. Like, remember in Computer Science 101 when you were trying to write a linked list, and all you cared about was, can I get it to work, right? No other concerns were bothering you. Later on, when I was programming professionally, I was exposed to Smalltalk. And one of the interesting things about Smalltalk and object-oriented programming was that they focused not just on making the software work, but also on expressing the problem domain, right? So you looked into the problem domain, you found the objects that were working, and you tried to show those objects in your programs. And so that led me to a career of doing training and consulting. And there was a particular kind of idea that was going on there involving using precise specifications. So if you're familiar with the Z specification language, there were things that grew out of that in the object-oriented world, like catalysis. And there was obviously work on design by contract at the time with Bertrand Meyer. So all these were not concerns about, can I make a program that works? But instead, can I think very clearly about the program that works? Am I confident that it's doing the right thing? So later on, when I went back to university, I studied software frameworks. And if you've used a software framework, you know it's both wonderful and difficult. It's wonderful because with a few lines of code, you can do very large things. It's very difficult because it's complicated to understand what small program you need to write in order to get these big things done. So software architecture was one of the topics at university, and my professors were involved with the creation of the professional domain of software architecture. And so I became interested in that as well. And I wrote a book about software architecture, which I think the primary contribution is it brings in a bunch of those ideas about how do we think about the problem domain while we're thinking about the software architecture. And most recently, I've been thinking about how we continue to do all those things we did before in the context of agile software development processes. I'm a big fan of the agile processes. They give us a lot of advantages. They help us deliver software reliably and get it into production quickly. But it doesn't leave a lot of time for us to think hard about the problem like we used to do. So that's a big topic here. We'd like to be able to think clearly with our software. Now, we've done that before with object-oriented analysis, where we think about the problem, and in software design, where we think about the technical design and the quality attributes that we're trying to achieve. I come at this particular problem thinking that we cannot exclusively look at software engineering to find a solution. We need to intersect that with the fact that we are living, breathing human beings. We're better at some things than computers, and computers are better at us than other things. So if we only try to solve the problem as a computer would solve it, we're going to miss part of the things. So we really want to build great software, but it's hard enough just to do it by yourself. It's even harder when you have to do it in a team, and it's harder still when you elongate that over time and you have to deal with the mistakes you made yesterday. So how often do we succeed at doing those things? I would say that far too often we end up with software that's overcomplicated. When you have to work with it, you get dragged down into the fussy details of the program. It's hard to think about the big picture, about what's going on, whether the big picture is the architecture or it's the features that you need to build. And you end up with some people on your team becoming experts in parts of the program while you're an expert in a different part of the program. Every once in a while, though, we do succeed. Maybe it's earlier in the project, or maybe it's in projects we work on by ourselves, and we end up with software that's actually easy to understand, that helps you think, that is wonderful to create. And I can't overemphasize this, because if you've experienced the joy of working with a program that actually is helping you, it's a lovely experience, and you want to get back to that. So, how do we get to doing the thing on the right-hand side more and more? That's what we would like to be able to do. I think in order to understand that, we need to talk about something that's kind of complicated. It's a topic called theory building, and I learned about it from an essay by Turing Award winner Peter Nauer. Now, please have sympathy for me. I'm up here talking to you about understanding software. You're all very hungry and would prefer to go to lunch, and I'm having to talk about thinking about software. Okay, so this is getting pretty abstract. So let me try to be as concrete as I can. This is the introductory paragraph to his essay. It says, "Programming properly should be regarded as an activity by which the programmers form or achieve a certain kind of insight, a theory of the matters at hand." And then he goes on to say something very surprising. This suggestion is in contrast to what appears to be a more common notion that programming should be regarded as the production of a program and certain other texts. So he's basically saying the important part of what we do as programmers is to go into a problem domain, understand it well enough, structure it, figure out how you can solve that problem, and it's less about the typing of the program when you're all done. So, he distinguishes two different kinds of things that you can know. You can know that something is true, and so if you were thinking about addition, you might think about memorizing an addition table. You might know that 3 and 4 is 7. But he distinguishes that from having a general theory of something. For example, a general theory of addition would allow you to add arbitrary numbers. So what we're shooting for when we build software is a theory that underlies the program, not a bunch of facts that cause it to work. So there was a great shift at some point when human beings understood the ways that the stars and the planets moved, and we shifted from this idea that the sun revolved around the Earth to the other way around. And it wasn't that you couldn't deal with astronomy the old way, it's just that it's far easier to deal with astronomy in the new way, where you see the simplicity of the diagram on the right, okay? And the reason I bring this up is that if we want to improve as we go along, we have to improve our theories as we move along. And as those theories improve, they allow us to think more clearly about the problems. So getting back to Peter Nauer's quote, where he says that programming should be regarded not as the production of a program and certain other texts. What he's emphasizing is the valuable part of what we're doing is the producing the theory, not the typing of the theory into the program. So just for comedic effect, I've put this in the heads or the words of the pointy-haired boss from Dilbert, and he says programming should be regarded as the typing of the program. And I often feel like the guys on the right-hand side. Now, I know you get a lot of snow here in Israel, but that's a snowball. And if you roll a snowball, it gets bigger and heavier and harder to push. The longer you push it, the harder it gets to push. And I feel like that's what's happening a lot of times when we have software, is that we start out with something that's manageable. Our human abilities to keep the complexity under control are okay, but unless we evolve the theory as we go, it gets harder and harder to make progress. Now, I'm not unaware that there are pressures to develop features because that's why they give us money to write programs. But we also have to recognize that there's a give and a take here, that if our theories are not improving, we will eventually not be able to deliver the features that we desire. Here's a problem. Regular machines cannot express theories. Software can express theories, but regular machines cannot. So here's an example. If I ask you to build a traffic light, and I'm talking about the actual machine of the traffic light, you're going to have to think about cars and lanes and turns and whether something is fair or unfair. okay? You're going to have to think all of those thoughts. But if you're just standing in front of a traffic light, the traffic light doesn't tell you anything about those thoughts or that theory that you had about the traffic light. Does that make sense? The traffic light itself embodies those ideas, right? It may, in fact, be fair about who gets to go through the intersection, but it doesn't tell you what you need to know in order to develop that traffic light. Here's another one. This is a rocket engine, and I've always wondered when I saw these why it has that spiral around the bottom. And one day I was in a museum, and the little instructions or the little text below explained something to me. Does anybody know why the spiral is at the bottom? Okay, good. So it wasn't just me. It turns out that the bottom of the engine is very hot. Right? Because we're burning things and so forth. And you've got compressed oxygen inside, liquid oxygen inside the rocket. So what they do is they circulate the liquid oxygen around in that spiral, which absorbs the heat and allows it to expand into a gas. And then when you... Is it working? There we go. When you burn it, you've served the purpose of cooling the bottom part and also taking the oxygen from a liquid to a gas. Okay? Now, the reason I mention this is that you can stare at that engine for a very long time and you will not be able to derive the theory that the people had that designed the engine that way. In fact, if you were building an engine, you might stumble across the same problem and then stumble across the same solution and then go, oh my goodness, somebody else did the same thing, okay? But the problem is that the machines themselves do not reveal the theories to you directly. So, the designers of the machines themselves have a theory, and they build machines that respect that theory. But we can do something better. In software, we can express our theories directly, and we should take advantage of that. And the reason we should do that is because it's hard to think these hard thoughts unless we're manipulating those thoughts directly in the software. So there's a thing, and I hope this translates, it's called a Rube Goldberg machine, and it's an example of a machine that does some relatively simple task, but it does it in a non-obvious way. So I hope you're enjoying the little animation of the stuff that's going on. One of the things when you ask the question about, like, how does this thing work, it's difficult to describe how it works without talking about each individual interaction itself. Like, there's no summary of what this machine is doing other than the conclusion and all of the individual parts, okay? There's no theory that underlies how this works. And the reason I bring it up to you is I find too often that programs that have evolved for a little while start to resemble these Rube Goldberg machines, okay? And they might have started out as like, I can master this complexity. And then after a little while, they get a little bit more complicated and you have to ask around, like, why does the program do this surprising thing in the middle? And maybe the people that have been around for a long time can start to explain it to you, okay? But eventually, you end up in a situation where the software is doing an enormous number of things. Very few people understand why it's doing things. You become afraid to change things because you don't know what the implications are going to be. And basically, there's no theory that explains why it's doing what it's doing. There's no intellectual control over the software anymore. Okay. Now, at the risk of beating this one to death, in the very top left corner, you can see a little bit of orange, and it's sort of bouncing up and down. Okay, do you guys see that? Maybe there's a laser on this somewhere. No, I don't know. No laser. Okay. So in the top left, there's a little orange. Okay. I would say that in a way is acting like a spring. Do you guys know what I mean by it's acting like a spring? Okay, it's a little piece, and when the ball hits it, it bounces. Okay. Great. Acting like a spring. That's really what we want. What we want is to be able to have some language that we can use to communicate with each other. We'd like to be able to say, there are kinds of machines called springs. We can characterize those machines. So for example, if I push down with a certain amount of force, it pushes the spring, it moves the spring a certain amount. I have a concept of elasticity, which means that it springs back to the original position. And I have a concept of deformation, plastic deformation, that if I push it too far, I've broken the spring and it doesn't come back the way it was. And the reason all these things are interesting is that this theory is bringing a kind of shared vocabulary and a shared understanding and a transferability between different problems that is very valuable to us. So this kind of theory helps us to think about things. So for example, many springs you've seen are in a circular spiral fashion. Does it have to be a spiral? Another question, you're like, what are the limits of this spring? How far can I push it? When do I reach the limits of plasticity? So these are all good questions, and they are not something that you ask when you're looking at a machine like this, because you sort of just give up, and some sort of higher critical facilities, you forget about them. But when you start analyzing problems like this and you're searching for theories, you stand a chance at being able to have intellectual control. The same thing happens in car engines. Has anyone noticed that every year our car engines get better and better? They're an incredibly complicated machine, but what's going on is that the developers of car engines are improving their theories year after year. We teach automotive engineering in the schools, and I'm sure that every one of the companies that does car engines has an internal set of expertise and theories about how car engines work. So one thing to notice here is that while the machine itself is visible, the theories are invisible. And it's important that we focus on some of this invisible stuff in order to be able to make progress in our field. We'd like to be able to think big thoughts. There's a concept called supervenience, which is something you probably will have thought about at some point, but maybe you haven't come across this word. The idea is that there's a stack of abstractions, starting with very, very low-level things that involve physics, and say one level up from physics is chemistry, and another level up from chemistry is biology, and maybe up from biology you might consider sociology and psychology and then sociology. Now, what happens if you try to solve a psychology problem using physics? It's not a terribly helpful abstraction to help you think about a psychology problem, okay? And so the reason these things end up being distinct disciplines is that they bring their own theories to the table, theories that help you solve the problems that are relevant at that level. So what you'd like to be able to do when you're thinking about your program is not think about the very lowest level, most concrete things. You don't want to think about what bits go into register AX. You want to think about the abstractions of your problem domain, whether your problem domain is how to get traffic flowing, or to launch a rocket, or to run an engine. Whatever the problem is you're trying to solve, you want to choose the right level of abstraction. And what happens in our programs is that it becomes very tempting to use the lowest level abstractions as the common denominator between programmers and programs. And so you find a lot of programs with very simple data types right out of the programming language. But using those primitives makes it hard to talk about the stuff that you want to talk about. So for example, the traffic lights. It's not a very good traffic light if traffic only gets to go in one direction and you starve traffic in the other direction. So you have a concept of fairness. You can't talk about fairness directly with integers and strings. So you need a higher level concept. Your program could express that. So let's see if we can do that. We want to be able to think using our programs. So what I've been doing for the past couple years is I've been working with the teams that I work with to write programs, and we're trying to make sure that our theories are expressed in the code as much as the code is giving features back to the company. And the way I think about this is the overall goal is to create a rich and expressive set of types in the programming language that we can operate simply. So some of the things from domain-driven design and extreme programming, I'm just adopting wholesale. That would include making sure the nouns from my problem domain and from my architecture show up in my language. So what I mean by that is if I have customers and accounts in my problem domain, you're going to see that in my language. If my software architectural style has clients and servers or microservices, you're going to see that language in my program. So I make sure those things lined up. Of course, there are things that I can't reveal, and I use JavaDoc to reveal those. Now, that's just talking about the code itself. I need to also work with the people on my team. And so how do I get the people on my team, some of whom have just come from university, to start seeing the theory the way that the experienced programmers are seeing it? One of the things we use is code reviews. So code doesn't go into the system unless it's been reviewed by someone else. And when code gets sent to somebody else, you have a great opportunity to ask questions. So things that are obvious to you when you're typing the code are not always obvious to somebody else. Just the same way when you write an email, it might seem obvious to you, but might be not clear to someone else. So the code reviews are an opportunity to ask, hey, why does it work this way? I don't quite understand it. Can you give me some context? And in fact, don't just tell me right now. Can you plow that back into the code? It can also be used to fix misunderstandings across the team. So if somebody's reviewing code and they said, hey, I thought it worked like this, the person can respond and say, no, actually it's working this other way, and like the theory evolves with the programmers. And the overall goal is to make sure that all the programmers are taking the theories that are building up inside their head and they're getting them into the code, and the code is getting better all the time. One of the things I noticed during our stand-up meetings that I was generally running is that I would call on different people and ask them what they're working on. And what would happen is that the rest of the team, when it wasn't their time, they'd sit there reading their phones and would be sort of bored about what was going on in the status meetings. So I tried something and it worked really well, and I'd like to share that with you, which is that I inverted the script. What I did was I put somebody else in charge of running the meeting every single day. So a different person, it just rotated every day. And what that person was in charge of doing was asking the questions that I would have asked, okay? So for example, if somebody said, on Monday that they were gonna get something done by Tuesday, but here it is, it's Wednesday or Thursday and they're still working on it, the question would be, hey, was that more difficult than you expected? Did you run into some trouble? Did it not work the way it's supposed to work? And so I would ask the leader, hey, what's going on? And then they would go, after a couple times where they didn't know the answer to the question, they would be the ones asking the question in the first place. And so they all became very engaged in understanding what was going on and why. So another thing that I found that really helps to think clearly is not programming in 1960s programming languages, okay? So many of the simple computer science 101 kind of constructs that we learn, that we can implement a linked list with, for example, programmers don't necessarily go beyond those because they work just fine, and they worked just fine in the 1960s. However, things have gotten better. We have invented new ways of expressing our intent very clearly. Now, I'm not saying that you want to rush out and use the most advanced things from every programming language. That's not what I'm saying. But I am saying that these things were invented as ways of expressing ourselves clearly and succinctly, and it would be a shame if we didn't take advantage of them. For me personally, it's been a lot of fun with the modern versions of Java to be able to use first-class functions, and it really dramatically improved the quality of our code. So one thing that people often complain about is that, look, there's design intent, there's software architecture advice. It's really hard, maybe impossible, to express that in the code. And it reminds me of a story that my advisor told me, which is that he was working on static analysis tools that were trying to check for safe concurrency. And he said, people for a long time looked at the halting problem and said, you can't statically analyze code, you shouldn't even try. But what we found was that most code is not written in a pathological way. It's not written in such a way that you can't analyze it. So what they found, and what you guys probably experience every day, is that your IDE tells you that, like, watch out, this variable could be null right here. That's static analysis helping you out. In the same way, I find that an enormous amount of design intent can be expressed in the code. So it's true, I can think of examples of design intent that's hard to express in the code, but I flip the script on this one too and say, I find most things can be expressed pretty well. So in conclusion, I was really excited to find Peter Nauer's essay. I thought it was a real eye-opener, where he says the important parts about software development are the ways that we analyze the problems and come up with theories that explain what's going on. If your source code were deleted and you still hold on to the theory that explains how the source code worked, you can rebuild that source code in a fraction of the time. And so this is what he means when he says the important part is the analysis that builds up the theory. And if we build up our theories correctly, we're going to end up with code that lets us think very clearly. These theories are hard to talk about, but they're critically important for us to talk about. It's much easier to talk about, it's Monday, how many story points do I have, what are the features I'm supposed to be building this week? But what happens is, without attention to the theories, you get a whole mess in your code. You end up with not very good theories. It's not a whole lot of fun to write code anymore, and over time it becomes harder and harder to deliver code. There's really a duality between thought and the computer programs. If you write a succinct computer program, there's really no other better way to explain the computation that needs to get done. What you really are going to try to do is figure out what your theory is, express it in software. The old way we used to do that was with long design phases and big binders full of UML documents. It doesn't seem like we're going back to those old days. And in fact, there was a lot of effort that was wasted. I think the better answer to today is to embed our theories in our software and use these team processes to ensure that the entire team is building and understands the theories that our software is helping us with. And with that, thank you very much. Let me know if you've got any questions. Yes?
I saw that you used Z a long time ago. Have you had any experience in using any of the more modern forms of, I would say, formal verification tools?
No, but that sounds very interesting. Yeah, actually, yes, I've played with Owly a little bit. I've chatted with Michael Jackson at a conference a couple years ago. Not Michael, Daniel Jackson, who built it, yes. Yes. So some of those things are also, you can consider them to be building blocks. So if you look at what an IDE does today for you, there's an enormous amount of analysis going on behind the scenes. And the more advanced your abstractions are, the better the computer can be about telling you things. So for example, I mean, like, if your program is really doing very low-level moving around of bits, you haven't expressed enough intent that the analysis can help you out. But as soon as you get up to some higher level, for example, it can tell you that the types don't fit right, okay? Or there's a path through your program by which some bad thing happens here. So I think there's a nice connection between those kinds of formal underpinnings and the emphasis on complicated, interesting types that reveal the problem domain you're working on that I'm advocating here.